Vision craft. Crafting clarity from complexity.
Perspective. So check whether it's working or not. So I hope you can see the screen. And yeah, this is MATLAB. So let's open this. Okay. So today, so first of all, I'll introduce myself. I'm Prakash. I'm presenting my M.Tech term assignment under image processing and computer vision. So I do my M.Tech in NITK. So my topic is EEG-based brain-computer interface using image processing. Today I'll be presenting a conceptual overview using slides. Then we'll go to some mathematical details using LaTeX file, and I'll finally show you live demo in MATLAB and EEG. So we'll be using that. Okay. So first, we'll have a decoding thought on EEG and BCI journey. So basically, EEG is electroencephalogram. So basically, the frequency measurement of the frequency measurement of brain frequency, like whatever the measurement we do for brain, that signal is called EEG. And BCI is brain computer interface. So welcome to the exploration of electroencephalogram and brain computer interface, and this presentation will guide you through the intricate process of translating brain activity into control signals, highlighting key methodologies and the profound impact of the rapidly evolving field. So basically, before going to the concepts, I think by this time you know what is EEG. It's the brain electrical activity we through scalp electrodes. It captures oscillations in the microbit range, reflecting the synchronized activity of large population of neurons. So for BCI and EEG, they usually use non-invasive, portable, and relatively like inexpensive signal source, we can see. So yeah, we'll go to the next thing. So this you can see electroencephalogram. It shows it's a non-invasive thing and a mechanism. So you can see this is an AI generated image, and you can see an example. So basically, we'll need minimum 32 electrodes to properly, measure a brain-computer interface, and the BCI definition is there. Will be enabling direct communication between brain and external devices by decoding the EEG signals. Information, the EEG signals will be from around 1 to 5 hertz max. Usually it's around 3 hertz, and there will be a lot of other data in that too, which you'll be seeing in the live demo, which I'll be showing a data set of an EEG signal and how exactly is it, we can be using it for analyzing, like how image processing techniques are used for analyzing how exactly like frequency domain is changed to, spatial domain and all these things. So our research focus will be on motor image EEG decoding using EEGLab and MATLAB. EEGLab is a module in MATLAB. Okay. So I'll go for the next slide. So yeah, so there are these rhythms which you need to understand before entering the concept. So you have an idea like what is brain-computer interface. So it's basically decodes the neural activity and translates it to commands. So there are basically 5 rhythms, where the delta rhythm is from 0.5 to 4 hertz. Like when you sleep, if we record it when you sleep and all, no, then that rhythm just point of view, I'm just saying this. And theta is 4 to 8 gigahertz, like when you are in meditative state, concentrated, like listening in class properly and all, it comes in theta. And the prominent during relaxation and all, it goes to 8 to 13 hertz. So these are the frequencies which we are saying, but usually recordings are in what do you say, we get it around 3 to 5 hertz only, the frequency range, because there's a lot of skull is there, and a lot of internal structures are there. So you can see the anatomy of a skull, so you'll get a clear pitch idea, which will not be discussing. You can just Google it. So you see the prominent actions are this alpha and beta rhythm only. Why I'll say, because these are the major things which we can do. Like it comes in motor imagery, like eyes closed, like thinking, watching, seeing, or what do you say, concentrated stuff, moving hand, all this comes in motor imaging. And there is gamma, which is 30 to 100 hertz, like higher conjugate density with like tongue, eyes, sinuses. These all comes in gamma, which we are not speaking about in today's class. So coming to the next slide, how we can do this, what is the procedure. So I'll give this in this PPT. Will be showing you an basic overview, and we'll study in detail once we go for the latex file. We'll be showing it in the upcoming presentation. So you can see there is an experimental paradigm and data setup. So basically fixation, cross, Q presentation. I'll be explaining it in detail once we get to the demo. So these processing I'll be showing. We'll import the data, we'll be dereferencing, filtering, and artifact removal and all. I'll be showing it to you. It's power spec, and these are a few parameters. So I think we'll go to the main thing. Just a second. Yeah. So yeah, we'll be seeing signal processing and analysis, filtering and application, and abstract and all we have discussed. Okay, frequency bands and everything is discussed. And once we explain this, I'll be again explaining before going to the, what do you say, the demo. I'll be also saying you what we are doing and how we are doing, so that you'll get an idea when we are doing the demo. Okay, so the overview of an electroencephalogram, like in detail, it was first recorded by Hans Berger in 1929. EEG has involved like lot of cornerstone techniques of non-invasive measurement and of the neurons, not other electrical signals or electronic whatever is coming in your brain. So in these notes, you can see how EEG is modeled as a combination of neural sources and noise. The observed EEG at an electrode, it can be expressed as EEG I of t is equals to ERP of t plus noise of t. I'll be showing it. I think I have written this. And the fundamental model which explains this. Wait, let me go. So yeah, you need to know few signal theory fundamentals. Like continuous time signal. What is a continuous time signal? It is a real-time valued signal of t. It's a Fourier transform of x of t. Is x of f is equals to integral of minus infinity to infinity x of t power minus j 2 pi ft dt. So you need to remember. Next, discrete time signals and sampling. So we're sampling a continuous time signal at period t, or ts you can say. Let's take t. The discrete time sequence will be like, the frequency is inversely proportional to time. So you'll get x of n is equals to nt of s. And sampling theorem, it's Nyquist-Shannon sampling theorem. You can just study. And the characteristics, this I have already explained in the PPT. You can just have a glance. What is the range and what it is. So I've said the movement reactions, like in gamma it's given like EMG contamination and all. So even the prosthetics what we see in real time life, you have seen a lot of prosthetics which works on EMG and EEG and all. We have a lot of development is happening in medical field. So all these prosthetics they usually take this gamma range only. So basically if there's a hand and there's a hand movement, so this hand movement it is basically recorded from this segment of signal only. So basically these whatever movements we are doing, this comes in gamma. So that's another application, doesn't come in image processing, so maybe we'll see it in another video. So yeah, you need to know few things like signal power and energy. The power of a discrete time over n samples will be 1 by n, sigma of n is equals to 0 to n minus 1 x of n whole square. So these all are like just theories. You can just keep it in mind, or you can just Google and see based on how we are going to develop the thing. And there is power spectral density, where xx of f is equals to limitation of t tends to infinity 1 by t mod of xt of f whole square. And there is a discrete Fourier transform, and there is a twiddle factor for this. You can refer it. So now we'll go for the major thing where I was saying how exactly we are doing ERP, event related potential. Like if there's an event, like you are blinking your eye, you are moving your hand, so these all are events. So what we are doing for it. Okay, So this ERP basically represents brain frequency at a time locked or phase locked in part of events, like in that specific time or in a specific phase, like you're sleeping or something like that. So as I said, the ERP signal mode is mentioned as EEG-I of t is equals to ERP of t plus E noise I of t. So I'll be showing this like in reality how it looks when we analyze. Okay, assuming that the noise is zero mean and independent across the trial, it's not dependent on any of the ERP values, and it's an averaging across the trials. We have a lot of trials. So yeah, that is the thing, and the fundamentals explain all these things like averaging and SNR, all this stuff. So already I've seen the sampling and discretion above. This is the average and SNR improvement, signal to noise ratio improvement. It's really necessary to increase the signal to noise ratio because there will be a lot of noise as we are not directly taking the data from the source. So there are a lot of in between things like the electrodes, the skull, the internal fluid, everything creates noise and attenuation. So it's very necessary to increase the quality of SNR, signal to noise ratio. So as you can see, for the given n trails, the average waveform would be like x of t is equals to 1 by n, sigma of I is equals to 1 to n, xi of t extension. So you can check the variance and all. Fundamentally, the fundamental model explains why averaging across trails improves the signal to noise ratio by variance square by n, which is equivalent to 10 log base 10 of n dB improvement. So this is what it is. Next, ERP extraction workflow. So basically how you will extract the ERP. So that is also there. And there is also like filtering and all, which we'll be seeing now. For ERP extraction, first you need acquisition high quality recordings. There are BCI, lot of BCI technology and lot of BCI machines are there. You can just Google and see a lot of stuffs like and you can measure, like maybe I could search for you. So there are machines like these. You can see something like this. So we'll be also showing you now in upcoming thing like how this representation. It's very really interesting. Once we go for the demo. The theory is a little boring, but yeah, but we need to know the basics before going to the theory. So now you get an idea how the data acquisition is done. So we get data for this, and usually these data are in billions, so we can't process this in what do you say? We can't process this in CSV, Excel, or anything like that. We need to put it in a higher format like .mat. Like we have workspace in .mat, or we have .set file, and a lot of things. A lot of other formats. And in pre-processing, we will be using bandpass and a notch filtering. Like we need to downsample the system if necessary because of the data. And epoching, extracting all the windows. Who knows AIML and all usually knows what is epoching and all. Usually I'll extract all the windows of the stimulus on set, like pre and post periods. And there will be a baseline subtracting the pre-stimulus value, like we'll have a value before stimulating the system, so that will be subtracted. And artifact an ICA, which is like removing the noisy trails or components, basically noise removal. You can use filtering for that, and averaging obviously. So this is an illustration of figure of an ERP waveform, and I'll be showing this in real time also, how exactly it works. So this is a synthetic ERP waveform of a canonical component of P100, N100 and P300. Okay, yeah. So we'll be going for the next topic, which is pre-processing and filtering. So why do we need pre-processing is a very important thing, because it improves the SNR and reduces the confound causes by the artifact. Basically it decreases the noise ratio or noise artifacts in the frequency which will get, because it's already a very low frequency signal, and we need to have almost like a minimum 80 to 90% good signal. So it's okay to it's very necessary for the pre-processing segment. And then we'll also learn this digital filtering theory. So basically there are two major classes, FIR and IIR. Okay, you know the FAR and IR filters. So the FAR filter of order m can be defined as y of n is equals to sigma k is equals to 0 to m h of k into x of n minus k. So the FIR filters have exact linear phase when coefficients are symmetric, which preserves the waveform shape. Okay, in IIR the same thing. It uses a feedback system. That's okay. You can, once we get into the demo, you will get to understand what it is exactly. So yeah, the IIR filters usually they give sharp transitions with lower order, but generally have nonlinear phase. Okay. So that is the thing. So filtering. So to suppress the power line noise, a notch filter at 50 hertz is applied. There's an image in 4.3. I'll show you like this. Okay, there's a notch at 50 hertz is applied. Basically, what does the FIR filters are preferred due to its linear phase and stability. So that is there. Okay, in notch filters you can see that to remove the power line interference from 50 to 60 hertz of a second order notch can be used, like h of z is equals to 1 minus 2 cos omega naught z inverse plus z per minus 2 by 1 minus 2 r cos omega naught z minus z per minus 1 plus r square z minus 2, where the omega naught will be 2 pi f naught by fs and r will be the control notch bandwidth. Design examples are there. This is what I was explaining. And next, I think we'll go for ICA decomposition. It is chapter 5 we'll be having. So artifact removal techniques, which is ICA decomposition. So the ICA model is expressed as x is equals to a dot s, where x is observed EEG. The mixing matrix and s are independent components. By estimating the unmixing matrix W, we recover sources as S is equals to W dot X, which enables the separation of the artifacts from the neural signals. Like you can see the sources. This is what I was saying, the independent component analysis ICA. So yeah, so basically ICA assumes that the observed data, X, it is a mixture of independent sources, whatever source we are getting. So that is what I was speaking about. Okay, and the next will be chapter 6, which is ERP components. So these components are like sensory components. It changes based on every requirement, mismatching detection techniques and all. We'll go for spectral analysis, which is chapter 7. So classification and machine learning, you can use machine learning. It's easier rather than manually doing it. Manually doing it is a hell lot of work and programming and classification and all things. And features of ERP classifications often include like time domain features, frequency domain, and spatial features, basically channel averages and all. So the power spectral density is estimated using Blend's method. We segment the signal, window it, compute Fourier periodograms, where smooth variance provides robust frequency domain features. Like you see the Wells PSD, power spectral density. By averaging the periodograms, you overlap the windows for a segment of x of n, where the estimation formula is given. So this is the thing. The next thing will be the frequency representations, like the dimensionality reduction and all. You can just study. I'll be uploading this in the description. And you can use a lot of classifiers like SVM support vector machines, LDA, IRP, and a lot of things. And the real-time applications, you can see signal acquisition, preprocessing, feature extraction, classification, control interface, and all these things, and latency and computational constraints, and brain controlled wheelchair, prosthetic hand. All these are one of the applications. So we will close this, and we can go for the demo, and I'll be uploading this so you can read it. We'll close this and we'll start the demo. And yeah, these are a few papers you can refer. And there are a lot of data actually for things you can do it. Okay. Coming to again the thing, as now we studied about the power spectral density and frequency analysis. That's what the Wells method we are using. So in EEG-LAB tool, we'll be using the spectrotop function in PSD. I'll be explaining the code. I'll be showing you the code also. So you see the feature extraction method. The feature extraction method. We have common spatial pattern CSP, a bandpower features, and we also have time domain features and all. You can just study this. I'll be uploading this also. So the classification algorithm performance you can see using LDA. We use CSP plus LDA, which is like optimal linear separatable data. You can see we'll continue. So the support vector machines we can use SVMs. People who are into machine learning and AI can understand this. Like the margin between the classes defined by the hardware plane will be like W power Rx plus B is equal to 0. It's like very strong non generalized form. And you can use deep learning, convolution neural network, RNN, LLMs also you can use, but I don't think LLMs can be imported in MATLAB. Yeah, you can use the program code, whatever you are comfortable with, like Python language, any language, not code, like Python or MATLAB. So we will be performing the example in MATLAB. So the evaluation will be basically measured using the accuracy, the precision, how much score we are getting, the confusion matrix. I hope you know the confusion matrix, what it is. Providing further insights, the subject variability, significant factors, influencing overall performance and all. So coming to the conclusions, our exploration will demonstrate EEG motor imaging signals can be reliably classified using spectral and spatial features supported by power tools with EEG-LAB. Effective processing, feature engineering, CSP, baseband, and advanced classifiers like SVM and CNN are crucial for robust BCI systems. Like in future, BCI will be the next tech, it's a generation, but it's a long run. But yeah, BCI is once if anyone miniaturizes BCIs and all, and that will be different. So yeah, in future it will be a big thing. So I think it makes clear an idea like what we will be doing. So yeah, I'll be sharing these files, and now let's go for the demo. Well, yeah, so we'll be going to the MATLAB. Yes, so there is a EEG lab which is basically signal processing, but why we are using that you'll get an idea. So yes, so first thing is we'll go to the MATLAB. We have the system here. So this lab was, the authors are from Institute of Computational Neural Computation from California, University of California. You can just, download it from online and upload it in MATLAB. It's better to use licensed software. So you can use a licensed MATLAB rather than crack, because sometimes crack doesn't run these systems. So this is a default thing. So there will be a folder. I can show you. I think. Wait a sec. Yeah. So this is that lab. You'll have these files. You'll have content. You need to run this lab EEG-lab.m file. So yeah, that .m file is this. So first you run this. It will open this, and we have loaded the data. First we'll load the data. You can load existing data set. Yeah, so I'll upload that data. The data is already uploaded. I am just showing it to you. So first I loaded the recordings into EEG-LAB. Not the important metadata here. The number of channels is 32 or 64. It can be. It depends on the sampling rate is around 500 hertz. Okay, and the total number of epochs and trials is around. It will be around 400. Like it's showing 384, but yeah, there is some noise extraction differences. Okay, it's fine. It will be around 400. Let's make it an approximation. And always we need to check the EEG straight and the EEG N band the right way, the downstream parameters. it depends on the fs and n channel. If we were like around 25 250 or 1000, then we should scale the window of filtering transition bands proportionally. Like sampling theorem remains, no, f of s is less than or equal to 2 into f of max. So to get it done, we need to do this filter transition band proportionally. So yeah, I'll be uploading that LaTeX file, which basically the document file. You'll get an idea if you read it. It has a proper steps. I have written the proper steps. Okay, so the dataset summary is there here. Oh, okay, this is not the data. Just a second. Because this data is not processed fully. So yeah, it'll take some time. Okay, we'll run it again. Not a problem. It will take some time. It will run. It will come. Just wait for 1 minute. It will run. It is processing. Okay, so this is how it opens, and we'll just load an existing dataset. Yeah, so now I think this is the first dataset. Actually, before I was working on another dataset, so it will get mixed up. So I just closed it and ran it again. Okay, so usually if you are running a new dataset and all, no, you usually close and do. This is already done. We have plottings. So we'll first go for the channel layout and the band channel section. So basically now the channel montage, the EEG, we can put it by name and also by number. Okay, let it load. So you can see, no, both are same. As we seen in that image previously, whatever we have seen, no, the scalp plotting, like 32 electrodes, what we have put in that BCI machine. So these are the channel locations. So these are the electrode locations, and one is on name and one is based on numbers. Now the channel montage, whatever I'm showing, the EEG-LAB interpolates and topographical grid for the scalp plotting. Okay, that interpolation is what turns discrete electrode values scalp image. When you feed to an convolution neural network, we'll use the same interpolation grid. So networks see consistent spatial patterns. You can see I don't know whether you can see my mouse. Yeah, so they are like electrodes here, here, here. I'll be showing the other outputs. So when we enter more depth into the analysis of this, you'll get an idea. Okay. So yeah, that's the thing. And the same interpolation grids are used in CNN, and consistent spatial patterns are used. So this confirms the channels like C3, CZ, C4 are placed correctly. These are the motor channels. Okay, so you can see the channels like CZ and all these things. So yeah, so these are the things and the parameters which you need to note. Wait, I'll just keep it open for some time. Okay, so the parameters notes like inch by inches. Interpolation grid, you need to keep EEG-LAB default. Spherical spline will be 32 by 32 grid typically. This yields a regular 2D image. Okay, bad channel threshold, visual flag by around plus or will be greater than plus or minus 200 microvolts. Long transistors of or flat lines will be there. It will be marked as removal, like 5% of the bad samples will be removed. Like even this, like only 30 electrodes are there. Fine, so this is that. Next we'll go for the draw EEG signal, what we are seeing, so that we can scroll the signal in this. I'll show you the data. So here now you got the point. What are these? You'll get an idea what are these. So here are the new raw traces, like with event markers and all. These are the important demo parameters, like plotting a window length, 10 seconds vertical scaling will be plus or minus microvolt for clarity. We can see the blinks in large frontal deflection of high frequency spikes. You can see the blinks here and all uh, from muscle artifacts. Decisions. So the decisions what we can take from this is if there are many large amplitude artifacts. If there are any large amplitude artifacts, marks the affected trails of epoch rejection later. Like in continuous data, no, it's non-stationary drifts. Then the plan of it high passes at 0.5 to 1 hertz. So what is the image processing tie in this is raw scrolling traces no are still in 1D signal, but we can transform this trial windows into an ERP image and spectrograms in 2D for image based classification, which I will be showing in the next thing. Right, so we have analyzed this. We can go for the channel spectral properties. These are the parameters we are setting. I've already set the parameters. You can modify it as per your requirement. Not a big deal. It can be done. So this is the power spectral density. So see, do the filter like we have done the filtering now. After filtering, no, filtering is critical. See, I'll apply the zero phase FIR bandpass for 1 hertz. Like it will be a high cut to 40 hertz, low frequency, low cut. I mean, it's a low cut. Okay. Why these numbers? For ERP and motor imagery, we want that MU band, which is like 8 to 13 hertz, and beta band, which is 13 to 30 hertz. Basically, it goes to 30 hertz preserved. Okay, so the frequency should be greater than 40 hertz. They will be greater than 40 hertz, or often EMG or noise, whichever is greater than 40 hertz. It's not EEG, it goes to EMG. EMG is like electromyogram, which like if you take this, if you take some signal from my hand, like from the shoulder, that will be EMG. So you can use an FIR, which is a linear phase with zero phase forward and backward filtering. So basically EEG Labs has an code called pop underscore EEG FILT new, uses a windowed FIR by default. So this is the output. So you can see the differences in the lower power spectral density as we given the formula in the previous LaTeX file itself, and you have the frequency range in the scalp. You can see in the images. I'm able to zoom. Yeah, I should be able to zoom. Okay, it's not, it's giving some delay. So this is like around 10 hertz. In 10 hertz, this is 6 hertz free range. This is 22 hertz range. So you can see how it is working in an image format, and this is a power spectral density graph. So that is the thing. So the parameters in this, the parameters in whatever we see here is like the locus cutoff is around 1 hertz high pass, the high cutoff is like 40 hertz low pass, and FIR we are using a Hamming window, which is like zero phase, like it's a default. So suggesting filtering order will be like EEG automatically selects, if you ask like to order 3 into f of s by low cut as an heuristic for fs is equals to 500, then lower cut will be 1 hertz. And order of around 1500 is typically like very sharp low, something like that. But effectively EEG-LAB auto designs the stability. We don't have the need to give big inputs and all. It can be done. And this data, whatever I'm saying verbally, is also there in the book. So you can see that. And they're like power line PSDs and all. Next we'll go for the we saw the spectral map properties. We're setting the frequency range from 2 to 50. Okay, just a sec. What is spectral map properties? So this is a next I'll be marking the reject the bad epochs criteria. Basically you'll put an amplitude threshold. Basically these are voltages only, no? So I'll put an threshold like plus or minus 75 to 100 microvolt. So strictly for ERP, the joint probability will be greater than 3. The standard deviation and the muscle burst will be around like 80 hertz. We'll remove the epochs with bad, which is like 25% of the bad channels, or replace it with interpolation. So the parameters will be like epoch amplitude threshold will be plus or minus 75 microvolts. In the ERP studies will be like plus or minus 100 microvolts, acceptable for MI. The joint probability outer line threshold is around 3.0 standard deviations. It has downsampling if necessary. So you can see this. This is a ERP image what we have got, and this is like the activity of the power spectrum of another activity of the ERP. Whatever we are seeing here, this is a little detailed. So you will get an idea like what we are doing. Okay. So in image processing time, and this downsampling reduces the image size for a spectrogram and ERSPs. If you are using CNNs or smaller inputs, speed training, keep consistent sampling across trials and all can be used. So basically image processing techniques can be used for processing this also. So basically it's not an image, but we are converting the data into an image format using the image processing techniques. So that is the thing. So we've seen the ERP image, and now we'll be seeing the channel ERP's other files, and after that we'll be seeing ICA. Just a second, I'll just plot the other file also. Okay. So you can see this, no? So this is ERP, spectral power spectral density, the latency. So I think you see all the together is this. So yeah. So the channel. So here you can use FFT. Showing you what it is. Okay. So this is without FFT, and I'll show you with FFT also. We'll change the settings. This FFT ITC place here. Yeah, it should get it done. Yeah, yes, there is a noticeable difference, like you can see with and without FFT. Fast Fourier transform basically. So this is an image processing technique which we can use. So you can see the difference in the graph also, like how it is and how smoothening it is. So this is one of the applications of FFT, which you can Google it and see, rather than me explaining it, because there's a lot other things also to go. So we'll be going for the ICA parameters. So ICA separates the source of x is equals to AS and solved by the W, such as S is equals to W dot x. So I'll run ICA now. You'll get an idea. Basically, the scalp map is the ICA. So this scalp mapping is also called ICA, algorithm data and all. And the best practice is to run ICA on continuous data after removing the noisy channels. Wait, I'll show you another data. Channel activation. So this will be the channel activation once you activate the channel, and the components we want to see. Yeah, so these are the components. So you know, right, in ICA we'll have a lot of components like pre-writing via PCA, and automatically many ICA implementations will be done. So these are like the components, like where what, and the data used to be continuous data, not epoch data. This is the continuous data, as you can see, like 110 110. These are the continuous data, so whatever is happening. And if you see, the n channel will be greater than 32 where the memory is an issue. So we'll set PCA to 32, which will reduce it to 32 dimensions only if necessary. So the minimum data length, is aims to assist the length, which will be 20, into the number of channels of the second data, which is the rule of thumb, which is the minimum. So the convergence tolerance, it defaults as a fine in EEG-LAB. If convergence fails, it increases from 512 to 1024. So this is basically a component inspection criteria. So the topography, like the frontal with the bilateral polarity, is likely like blink, is likely like blinking. If you see large brief deflections, if you see like, wait, I'll show you the data. If you see like large briefing deflections, like large deflections, it means a blink or a saccade, like like this. Okay, a spectrum like high power, like greater than 20 hertz, like you see sudden spikes, you see spikes here. If you see this one, two, you have sudden spikes here. So whatever you see here are like muscle artifacts, because those are the higher frequency, as we saw in the previous thing, like gamma waves and all, in terms of EEG. And the source location is like motor like lateral scalp is likely neutral. So we'll remove the components and the clear artifact, and we get a smoothened data like this. Here we have seen the previous data, like you've seen this. You can see how specifically we are able to divide. So this is done using the image processing techniques basically. You can see the difference after the processing of how we are doing. So this is on with time domain. So this is after the thing. I think I can show you the first image. Yeah, this will be little detailed in comparison. Yes, this is correct. So I think now you get an idea that how we are splitting each and every data point so that we can segregate everything. So basically remove the components, clear the artifacts, 1 to 2 blink components or something, then reconstruct the clean data. Then we, the IC component of scalps, it's highlighted in the blinking component, like before and after the ERP, showing like, you can see the artifact removal and all. So basically you will have everything here, right? So I think now we get an idea how exactly this is working. I know it's a complex topic. You need to, run the data 2-3 times to understand it. It's not that easy to understand first try, but maybe yeah, you can try it by yourself rather than watching this. That's a very good thing. Next, epoching and baseline. We'll see details to that. Before that, we'll be seeing the 3D and 2D modeling of the scalps. So you can see here how it is forming the waves and all the generated things after the processing of all the removing noise and all these things. So you can see the clear picture of how the signal is traveling from in each and every node or electrode. Let it load. We'll also run the 3D mapping of this. So okay. Just a second. So as you can see, this is a 2D spectral image processing. Like you can see all the data here. We'll go for the 3D also. So this will take some time for processing. So before processing 3D data mesh, you need to upload the head mesh of all the details. Like if there is a mesh, if there is a mesh, you need to get the details of the mesh. So basically, if there's a head, you need to have the 3D model of the mesh so that you can upload all the data files in that. So we'll do this. You'll get an idea once it gets computed. So you can see the 3D modeling data sets, like how it is converting and frequency domain data to and image spectral based information. We'll let it load for some time. We'll get an idea. Okay, so we have this data loaded. So you can see here, like we have all the 3D data sets. So basically, in ICA scalping, as I said, we have a template to match a classic components. Like so long of neural, main pipeline and ICA to all artifacts basically. So once you artifacts, you'll get a clear data. The best example is you can see this power spectral density compared to the density we had. And I'll show you the first density. Yeah. So you see the first data what we have had before pre-processing and the later data after the pre-processing. So you can see the data difference and the removal of noise and artifacts. So that that's how it's done. Okay. So yeah, so these are the 2D and 3D images of whatever data we are having. Fine. Okay. So next we'll go for component properties. So these are the component properties, like you have an offset of 0.479. You can see these calculations from LaTeX, you'll get an idea. So this is an power spectrum average line, like basically the average ERP, the waveform. The scalp topography will be at P300 peak. To convert this image for CV pipelines, you can export it to topomap as in grayscale 2D image on a fixed what do you call a fixed spherical grid. Example, if there is like 32 by 32 or 64 by 64, and normalize the values to zeros and ones, and keep the same interpolation grid for all trials. Like consistency is essential in this. So people for advanced level will use CNN or machine learning models, so you'll get an idea. To get the exact steps, you can in EEG, you can go to EEG-Lab's topoplot, and you can fix a grid scale like 64 by 64 or anything like that. So in this, the image processing also will create an proper thing. So we have already studied the power spectral density analysis and all, and component mapping. We'll go for the ERP images components. These are the parameters which you can see. These parameters may vary, depends on your requirement, like you can do rescaling or significant signals, amplitude limitations and all. So I'll be showing an overall view. You can study this in detail once when you learn. So let's say this is one component. Okay, so wait, I'll show you. Okay, so you see this data epochs, right? Let's say this is one component. Let's take FPZ. It will open. Okay, you see FPZ. So now this FPZ data component. This FPZ component is one of the component which we are taking, and after analysis, like it reforms us properly. It gives us the proper clean data. So this is after all and all those things. So this is also basically a power spectrum, like a parameter. Like basically there will be a window for 1 second, and you will compute the PSD via lens method. So lens method is again explained in LaTeX properly. I'll be uploading that. So apart from that, what is the tie-up for image processing? So there is a spatial domain in this, you can see. So the PSD plots and the per channel PSD vectors can be arranged as PSD images, where rows is equals to channels and columns is equals to frequency bins, where this 2D mapping is ideal for convolution neural networks and 2D texture descriptors. So basically, if you are going to use any machine learning model or anything for artifact rejection or noise cancel, noise removal or noise rejection, like gamma range or something like that, that time these kind of things will be useful. Next, time frequency we'll be seeing. We'll go for time frequency. So there is already I've shown you the time frequency with FFT and without FFT, and there is also a component based thing, like this is a component time frequency graph, and you'll also plot it using FFT also, fast Fourier transform. Okay, just a second, okay, so now you can see these two images. These two images are like these are the ERSPs. These parameters are for image regeneration or something like that. So for time frequency, we'll compute the ERSP with wavelengths, which is called modlet or STFT. So my parameters of frequency is like 4:1:40 Hertz. The number of cycles increasing from the lower frequency to higher frequency, which will be from 3 to 7, are to be balanced by time frequency resolution, where time window matching epochs will be like around 200 to 800 milliseconds. So the parameters will be like the frequencies from 4 to 40. As you can see in the graph, the frequency goes from the 10 log 10 base decimals to 50. So we can say it as 4 to 40, which is 1 hertz step. So in these wavelet cycles, we'll have 3 to 7 across frequency, like this called linear scaling. And you need to do a baseline normalization to plot the graph. So how you can do it? So baseline normalization can be done using FFT also, uh, and it should be related to the pre-stimulus version, like minus 200 is to 0 is a milliseconds is like a baseline normalization. The time resolution, it depends on cycles, except for 50 to 100 milliseconds resolution at 10 hertz. So this shows suppression and the beta rebounding and everything. Next we'll go for CSPs, which are common spatial patterns. Common spatial patterns. I'll be showing it to you. Okay, if you are comparing any plot now, you make sure that you have the previous data. I didn't have any data now. Maybe you can do it in future studies. Okay, so this is the largest ERP component of this EEG data, whatever you have, and this is the final version of whatever components we have. So now you compare this original data, each and every data together, like there are 32 nodes, and we are neglecting 2 nodes because they're like noisy and they're under frequency. So let us open this. So you can see this is the first data set we have. Now this is here optimized clearly, and this is a bandwidth, like you have this range. So this is an epoch window, whatever you are seeing. So this is basically feature correction and all, and it's classified precisely. So you can say it as an LDA baseline. You can say it as an LDA baseline. So this LDA is a numerical stability, no hyper parameters beyond shrinkage, like Leonid Wolf recommended automatically. So that is an EEGLAB specialty. You can use that. You can use SVM. The kernel will be linear. Kernel is equal to linear. C is minus 1 initially. We use grids like C belongs to 0.01, 0.1, 1, 10 with nested CV. So basically, if you go for CNN, like image pipelining and all, the transferring of learning with pre-trained data sets like ResNet 18 or MobileNet version 2, the input will be around 224 into 224 RGB data, which will be ERSP and Topo CSP channel stack and all. The batch size will be from 16 to 32 depending on the GPU. If you have a bigger GPU, it's better for the image processing of these data and all, because the data sets are very large. The learning rate will be like 1 exponential minus 4, which is an Adam optimizer. You can learn about it in Google. And the epochs for this are like 2250, like it's early stopping. Okay, so the data argumentation, no, it's like small time shift frequencies, jitters, horizontal, vertical flip flops, only if justified. So you should be careful, like flips may break the anatomical meaning, like if a small crops and intense jitter, the cross validation, the confusion matrix and all these things, that will vary. So I have not done the confusion matrix for this. Maybe if possible, I'll upload it in the description. Okay, fine. I'll wind up this. You can actually manage to use this data rather than learning it online. So yeah, so that is the overall ideology of, or an advanced point of view to how to use. Okay, so let's about this and give a summary. So what it is. So the summary is like we cleaned the data, we used filters and ICA, we added it. We had clean scalp images, spectrogram ERSP images reveals the mu and beta, ERD and ERS. CSP produces discriminative spatial mapping. We convert topoplots, ERSPs to images, fix grid and normalize and feed them to image pipelines like HOG or Gabor plus classical machine learning or CNN. In real time, we run this sliding windows to produce image frames and classification or classify them continuously. So these are takeaways whatever we are seeing. So now we have come to the conclusion. So the thing is, EEG is an full analog signal which we are optimizing, and we saw how we are optimizing and converting it to the spatial domain. So what exactly we are learning from this is, now if I will explain the EEG output image processing technique we used, why it matters. First thing is topological scalp mapping, which is an EEG plot. Like you see the 2D images and all, whatever we are seeing, we will get an idea. Okay, so this is the 2D image. This is a topological scalp mapping. So when it goes for spherical interpretation, like exporting it to 2D grid and normalization, applying CNN like transfer learning, or compute some Zernix movements or HOG for classical machine learning, it maintains spatial relationship between electrodes, and CNN learns spatial patterns. Example, lateralized motor activation, robustness to modest electrode shifts and all. As I don't know if it's visible, you can see the shifts of every signal in every node, so how it is at a specific time domain. So this in real time will be like a very beautiful image processing, like if you see it and all combined. Maybe that we can do in another day. Next thing is the ERP images, the trial and times heat stamps. Image processing, you can do it for 2D convolution filters, morphological denoising and CNN, etc. Next will be the spectrogram, time and frequency heat mapping. So that's not time, just a second. Time and frequency. This also you can see is also heat map only, like the potential and latency also will be considered as heat map. This is also spectrogram, it is also ERSP. So basically, to convert it to dB, you can apply color map, use pre-trained convolution neural networks, augmented by small time by frequency shifts using Gabor filter bank or 2D wavelet filters for filters. So why we need this is because it makes sure that it's visible for localized patches in the image. Like CNNs are excellent picking such localized patches. So these all are like the later applications, and these are already developed in MATLAB. People who can import it using this MATLAB files in Python are good. You can do that. I'll not be showing that demo now. It'll because the video length will be expanding. Next, you can go for the scalp maps, combining multiple channels. It automates lot of artifacts and all. No need to do this stuff mathematical. Now all we did here is using mathematics, right? You no need to do this mathematics and all. You can just give the training data set and try doing it. So it is easier for the system to train in terms of image rather than giving billions of data. Like this is how the the frequency runs. And coming to the concluding, converting EEG to whatever frequency, like image representation, it unlocks the full toolbox of computer vision, like full open CV and everything. Pre-trained convolution neural networks, expandability maps like GradCam, data augmentation, and robust image descriptors. And for any assignment, I demonstrated that signal processing and image processing together improves features, richness, and classification robustness for motor imagery BCI, brain computer interface. It can be used. So when it comes to the future scope, you can be like online transferring learning to adapt across cross subject variability. Let's say there is one subject in India and there is another who's expert in EEG or who's expert in brain analysis for any disease in some other. It can be easily mismatched. Like you can combine EEG and EMG and all these things, and hardware acceleration for sub-secondary latency in real time BCI. So yes, so that's it for today, and I'll take questions. So you can put your questions. I'll be answering it.